I said. Conversational.
Here we are.
G'day, Richard.
G'day, Ben. Welcome to Custom KTM Customs.
Thanks, mate. Thanks.
Well, I got a little bit of homework to do, trying to get the motor running. So we'll come back to that one. So what are we going to talk about today?
We've spent a lot of time talking about the control strategy for this bike, obviously for the last year or so. Oh, maybe it's 6 months, hasn't it?
About seems like
6 months. Feels like a year.
4 years.
Yeah. Yeah. So I guess we've been talking about this for a while anyway. So obviously we're really excited about having the boost separated from engine flow, airflow, and all sorts of things, and all the advantages that come with having e-turbo, cold air intake, and no radiant heat from the exhaust, and all those sorts of wonderful benefits.
Not choking off the exhaust because the turbo's in there, so we move it away. All those pluses and everything.
Yeah, absolutely. And obviously the beauty of this is it is a track bike, so our run times are 20 minutes. So we've designed the entire build around 20-minute run times. So we get full control of intake for an entire 20 minutes. Hopefully. Hopefully.
Oh, well, I mean, the worst thing is that we'll either run out of fuel because there's only 5-litre tank, or you run out of batteries, and we limp home under natural aspirated.
Oh, that'd be horrible.
I know.
Naturally.
How embarrassing. But there within lies the whole conundrum, because the Max ECU is a speed density based computer, ECU. And where our whole strategy is around measuring mass air, because mass air and tuning and fueling link hand in hand. So your speed density is a mass air flow calculated function. And it incorporates the map sensor, which is pressure. Intake air temperature, ambient air temperature, and a few of the dynamics in that, and your VE table is fundamentally it. So it gets feedback from the wideband sensor, so it's a feedback reactive type control center. Now, what we want to do is map out turn this motor into like a 600cc motor, which means providing air by volume. So how do we do that is the big question. And the only way I can think about doing it is to put a mass airflow meter into it, model up the performance of the electric turbo, so that we have an upper target, which is our theoretical target that we can set for the motor. And then we have a series of tables there that measure the difference between what the naturally aspirated side of it would be under normal revs, our target, and that difference is what is the extra component of air delivery that the e-turbo provides under some sort of control strategy. So this control strategy is really what's doing my head in.
And we've got it. There's a number of different ways we can do this. Different strategies. So it's about trying to merge the hardware with the practicality of riding a motorcycle and response to feel,
100%,
and also meeting these targets that we're talking about. So I think we may have mentioned in previous videos where we're talking about simulating a 600cc engine in the lower RPMs, and then slowly tapering back closer to the natural capacity of the bike at those higher RPMs. We
don't want to stress it out at the high rev ends.
No.
But we want it to feel nice and big bikey down at the lower torquier areas. So where your where your res a little bit lower, down in that 3,000 to 4,000 RPM, or 4,000 RPM there. And then as the motor naturally revs up, you can actually tune it. But, we've also got some physical limitations that we're not quite sure of the bike. We're still running normal head pressures, even though we're running induction air temperatures extremely low
Yep.
as compared with a turbo.
Yep.
So
their limitations we'll walk through as we bring these limits up and we start finding where they are.
Yeah, that's right.
Yeah.
That's part of the tuning exercise. How much advance you can put in, how much fuel we've got to put in, and the cooling of V85 and so forth. That all plays into it. But they're all unknowns. So what we have to do is probably give ourselves a way to limit that upper target, but a way we can actually adjust it when we feel more comfortable with it.
Yeah, that's right. So on top of that, on top of all that, we also have two control methods. We have a turbo that we can spin up to simulate an intake mass airflow or engine capacity.
Yep.
For the speed density folks.
Yep, and that's what drives the big volume of air, the turbo spinning up.
Yep.
Yeah.
And then we have another control mechanism, which is our wastegate.
Yeah, throttle body wastegate.
Throttle body wastegate. And that helps us fine tune and trim that pressure to just, I guess, give us, well, it's surge protection. And engine, so it's protection for the turbo.
Yeah.
But it also does allow us the opportunity to then fine tune some of those pressures.
Absolutely.
That's the strategy there too, right?
Yeah, that's the way I'm thinking about it as well. So that you can have the turbo spun up, depending on the riding platform that you're at the moment, where you are on the track and what speed you're doing, and whether you're feathering through a corner, and you've got half throttle or whatever.
Yeah.
You don't want that to be very boosty in its behaviour. You want it very, very well controlled. But you want the turbo to be nicely spun up, ready for when you come out of the corner, and you want that immediate grunt. And so your turbo plays the heavy lifting role.
Yep.
And your throttle body plays the I guess what we've used before, the scalpel, the fine, quick, responsive, based around your third control, which is your throttle. And your throttle's really the only piece of the puzzle that you've got control of fully.
Yep.
Everything else has to be complementary to how you want it to ride, based on throttle, based on a whole different other set of parameters that we actually have to map out.
Yeah, and I think as we've discussed this in the past, I think the way that we've talked about it that I like to visualize it is that with throttle response, the turbocharger is the slow responding in deaccelerating,
correct,
but quick to respond in acceleration. But that's more or less the methodology will apply to turbo response is quick to respond to throttle when it's applied, but then when it's wound off, we just let that response a little bit slower, but that's where the wastegate steps in for the quick response on the deacceleration. So it's acting quickly at that end, and obviously also quickly in the other end as well. So the throttle body's always acting quickly to respond to throttle changes, but the turbo is just there in the background, just creating those nice, clean lines so that it's not changing too much.
I completely hear what you're saying, and I think that's definitely the best way to go for sure. So if you're screaming down the straight, your turbo's spun up to where you want it, around that 70 to 80,000 RPM, and you've got wide open throttle, and you're getting near the braking zone, the first thing you do is you slam the throttle shut. You're not going to spin that turbo down. You're going to leave it up that top end there because you're in a transition in a corner, and you might only be there for 3 or 4 seconds before you come out of it. But you've got to deal with the surge that comes with that slamming that throttle. And hence the throttle body will just instantly, reactively sense that you're throttling off. It'll measure the rate at which you're throttling off. It'll then open up the dump valve in pure response for that. So that shockwave just never ever occurs. It'll just be exhausted straight out the throttle body. But the turbo's all revved up already. Maybe slowing down a little bit for when you come out of the corner. And then as you open that throttle up, it could be wide open, 75%, or you're feathering through the corner. It's got to behave in such a way that there's the difference ready to go, and the turbo spun up.
So if we've got our top RPM or top mass airflow target to simulate which we've referred to as Delta 1.
Yeah, the Delta.
The Delta 1 target, which is that optimum. This is what we think we can achieve.
Yeah, this is what the motor can withstand, and that's what our big target is. This is our 600cc upper limit sort of thing. Whatever so that profile might look like.
Yep. And then as you come through that corner, you've rolled off throttle, and you're rolling back onto throttle, and you might be at 40% or 50% throttle through that corner.
Yeah.
But as that turbo is winding down, or it's holding at that RPM, that throttle body is then also helping peg the mass airflow at the throttle position relative to that optimum, that top end delta.
So that to the motor's RPM as well.
To the motor's RPM, and that's that interaction. Then as that throttle winds up, the throttle body just continues to close until it's fully closed, and the turbo takes over. And once you're wide open throttle, everything's shut, and the turbo's at max.
Yeah, so we're controlling the turbo, the throttle body, the responsiveness of the E side, the electric turbo, based around mass airflow.
Yep.
And all of that then feeds into the intake, into the motor, which is then handed over to the max ECU that then tunes it, timing, fueling according to speed density, which is it's fundamental. So effectively, we are a pseudo controlling the motor's tuning by mass airflow, by mere nature of controlling how much volume of air it's going in and out at any point in time.
We're creating the atmosphere with which the bike exists in.
Yes, that's
right. The max ECU runs the bike.
Now I'm getting it.
And what we've done is simulated an environment with which it lives in.
Yes.
So
it has no control over that. We are controlling.
But we can control it precisely and predictably, which you don't get with a traditional turbo.
Yeah, that's right. Yeah.
You get a very, very unpredictable, violent sort of environment where we can create a very nice, cool, exactly pressurized
environment.
Well, pressurized or mass airflow, however you want to look at it. But
Yep, I think I'm getting it.
Yeah, cool.
I think, somehow we've got to do a bit of a brain dump of all of this and so that it makes some chronological sense.
Yeah, we've got to put all this in M-tune somehow.
Yeah, that's right.
Yeah.
So
to control all these things, but I think from a strategy though, that all works really well. You have that target mass airflow for the engine throughout its entire rev range, which almost like a volumetric table is quite static. The only thing that's dynamic there is a throttle response, which exists in that RPM range and that mass airflow range. And then the turbo is basically what delivers you, it positions you on that based on your throttle position.
Yeah. Okay.
Yeah.
I think I can get my head around that.
Very good, very good. All right, well, so what do we, I know you've been doing some drawing here. So, and you have put all this down into a from a naturally aspirated state of the bike. Stepped that through a few, establishing the boundaries. And the conditions, and then building that into a bit of a tuning strategy.
Yeah, correct. So you've got to baseline the motor against the parameters that it's going to be controlled by, and that's your throttle position, motor RPM, that consumes a certain amount of air, coming back to the mass airflow rather than the speed density. It consumes a certain amount of air throughout its rev range for a certain amount of throttle opening. So you model all those, and then you, over the top of it, build another map, which is the target, maximum capacity target. And then you compare that with your naturally aspirated line, with your target line, and that's the growth map from a 400cc to whatever we want to make it within the physical bounds of it. And so that gap is what we actually track with throttle going forward as a delta part of it. And
so with aside from the turbo control then, the turbo control and the wastegate control, essentially what we're doing is creating a volumetric efficiency table of a 600cc bike, sort of, depending on the rev range. But basically that's what we're doing. We're starting off at a 600cc, tapering it down to 500 and then 400cc engine. And we're just creating that volumetric efficiency table.
Yeah. And what we're doing is we're just using that table compared with the 400cc motor to then dial it up or dial it down depending on what throttle position we've got or what revs we are. And we're using the benefits of an e-turbo to deliver that volume. Yeah, cool.
Completely on demand. So
on demand,
it takes a lot of the challenge out of tuning a turbocharged engine out. Because you're essentially just tuning a very controlled 600cc motor.
Yeah, exactly.
You know, but we decide what that capacity is depending on the RPM of the bike and what power we want at what point.
Yeah, I like your analogy where we are building the environment in which the bike is going to breathe.
Yeah.
And then let the max ECU's speed density tuning deal with that as a separate entity completely. Yeah.
No matter how many times we talk about this, the penny keeps dropping.
Yeah.
I think I get it. I know, great. I walk away and then we come back and I'm like, yep. I get it again.
Yeah, that's right. Well, there's so many moving parts to the puzzle there, and every time I think about it, another little variable creeps in.
Yeah,
and you sort of got to try and get that within the concept of the whole strategy. But I think we've pretty much nailed it down.
Yeah.
So I think we have.
Yeah. Awesome.
So
all right. Should we have a go? Should we have a go at putting one of these? You know, I'm thinking that I'll just keep the tape rolling, but I was thinking, and I won't show this. We've got a bunch of colors, don't we?
Yeah, we've got.
So we could almost create that, you know, draw that, you know, Delta 1.
Oh, yeah.
Delta 1 table. And just upside down, isn't it?
No, it's just a triangle. Is the
Delta. Yeah.
That's
I didn't draw it very well. So your Delta 1, and then you have your...
Well, basically it's a graph.
You have your naturally NA line.
And there's your sort of mass airflow, which is what we're doing. RPM. And this is RPM here. 0, 9K, 0 to X, you know, which is equivalent to 600 cc's or whatever we want to make it. And there's your curve.
Yeah. So this is our
mass airflow.
This is our target mass airflow.
Yeah, this is
based on what we think that we can achieve with the turbo we've got, what we can actually deliver, and what we think the engine can handle.
This is your naturally aspirated one.
Yep.
Yeah. Yeah, and that's our Delta 1.
Yep.
Yeah, correct.
Yep.
And we have another graph. We probably drew that a bit too big.
Yeah.
Well, we can Delta 2.
Yeah, well, we can overlay. So, the Delta 2. But basically, what dictates all of this space in here is throttle position, correct?
Hey, this is a good graph because I am going to now overlay a different one. What have we got here? There's red and black.
Yeah, open a new one. Yeah, go on.
Get a green out. Green's a good colour. Green for gold. Go.
Green for go.
So here we go here. And green is for throttle response.
Yes.
So your throttle, say if we have down here. Good. So we're about 2K.
Sure.
And then we're winding up to there. So that's the range we want to operate in.
Yep.
And so we have got here mass airflow at 2K, we want it to be here.
Mm-hmm.
And at 9,000, we want it to be here. The naturally aspirated flow goes like that.
Mm-hmm.
So we have a delta target in amongst all that.
Yeah.
But the thing that influences how much of that we actually get is where your throttle position is in respect to the naturally aspirated point.
Yes.
So if you're going through a corner and you're at 4,000 RPM and your throttle is equivalent to what a naturally aspirated position is because you're just feathering through the corner,
yep,
then you don't want to be suddenly having this thing go up to the target.
Yeah.
So what we have a throttle which is sort of all over the shop depending on what rev you're at and what part of the track you're on.
Yep.
So here we have another variable that's called delta 2.
Yep.
And so that there is calculated as a percentage. Now, your wide open throttle position could be up here.
Mm-hmm.
So that could only be like 60% of what a wide open throttle position might be where
yep.
you are.
Yep.
So that percentage is how much of this you're going to actually pick up.
Yep.
Because that's what horsepower you are saying you want.
Yep.
Okay?
Yep.
So this delta 2 follows your throttle in relation to the naturally aspirated position and slices out a percentage of this target
mm-hmm.
to apply to the environment that the motor is going to live in, and off you go.
Yeah, and so that deals that brings that simulated environment up to those conditions too.
And also this here, that comparator there gives you the control that you want, knowing quite well that you've got this available,
mm-hmm.
but you only got this is what you want.
Yeah, that's right. You'll depending on rate of change of the throttle.
Yep.
Rate of change.
Yeah, rate of change of the throttle. So it's a PID controller.
Yeah. So as you come out of the corner and you clamp that on and wind it up, you will pull higher towards this target.
Yeah, so if you're coming out of a corner at,
mm-hmm.
let's say, 4,000 revs,
mm-hmm.
and you were feathering it here, and suddenly you go up to here,
mm-hmm.
and this might be wide open throttle.
Mm-hmm.
So at that point, your percentage is 100%
mm-hmm.
of your voltage reading at the naturally aspirated point versus where you are.
Mm-hmm.
And that then says, right, I want all of that.
Yep.
Ramp it up, close that throttle body off.
Yep.
Give me that volume.
Yeah, at which point either the throttle body wastegate's going to slam shut.
Yep.
And all of that air is going to be there.
Yeah. Yeah. Or it's going to feather depending on...
Well, we tune that rate of change, don't we? Yeah, so you don't get a violent kick.
Yeah, correct.
Yeah, you don't want suddenly 40 to jump to 55 horsepower in half a second.
Yeah, correct. Yeah. That's exactly
especially around a corner.
Yeah. Well, yeah. Well, that'll be all how your throttle comes into it, because you'll get a feel for the bike as you're feathering it.
Yeah.
And you'll bring on the rate from your throttle based on what rate of change you want to have based on how the bike's going to feel.
Yeah, that's right. Yeah.
So, but the key to it is that the turbo's spun up.
Yep.
The volume of air is flowing.
Yep.
The wastegate is actually helping you feather the bike correctly.
Yep.
And when you need it, and you ramp up the throttle to the position where you want it to be, it's then going to take that slice of that target out, and it's going to deliver that volume of air.
It'll be quite interesting to see this on a dyno when you're holding wide open throttle and quick shifting through gears, and you watching. It'll be very interesting to see that.
Yeah. The quick shifting through gears is where the throttle body response is going to come into.
Yeah.
Because we know that operates very, very quickly.
Yeah.
There's no way in the world the turbo can actually spin down and spin up again.
No.
And the whole purpose of the strategy is to avoid doing that.
Yeah.
So,
but watching those to map that on a dyno will be that'll be really cool.
Yeah, it would be.
That'd be really cool to see that.
Yeah.
To actually map. I mean, no, theoretically we can set this target, but to actually put that in and see what that really is.
I'm going to be really interested to see how a tuner tunes the speed density side of the max ECU.
Well, I don't think it's basically just volumetric efficiency.
It is.
It's a pretty basic tune, really.
Yeah.
Because we're controlling everything else.
The environment. We're giving him in the environment. He's just got to fuel it.
Yeah.
Add timing or take timing out and do all of those.
So the only complex thing is that he has the option to have. He has some options to tune, as opposed to, well, all I've got is this.
Yeah, that's right.
Which you'd normally only have.
Yeah, correct.
So at least this you can be like, well, actually, we could do this, we could do that. And that comes down to basically what we think the engine can handle, really.
Yeah, that's right.
You can always flatten it out by adding more, but maybe more isn't the option.
Yeah,
isn't the answer. Maybe more is too much.
Yeah. And you might want to have the motor running in the lower rev ranges for the majority of it and relying on low-end high torque.
Actually, that is also another interesting point, isn't it? I remember you talking about this, and I'm going to bring it up, even though this is getting long enough. But talking about natural torque of the engine, I remember you talking about an option about increasing the natural torque of the motor.
Oh, yeah, cam timing.
With the cam timing.
100%.
Yeah, no, so it's already a very torquey motor as it is.
Potentially going through that way, yeah, absolutely right.
So that way we're gaining the advantage of the E-turbo low-end torque plus increasing torque.
Yeah. So if it's all about breathing.
Yeah.
And because we're now removing any of the restrictions from the exhaust side, which normally the motor would be trying to push air out through the restriction of a turbo. Now that that's not there, and the volume of air coming in there is the environment that it breathes through. 100%. You could start working on cam timing and bring your torque curve way back in the rev range. That's a real possibility. Now I'm really keen to do that.
What a little weapon!
It is.
What a little weapon!
It does mean that we have to get some variable adjustments on the cam gears, both intake and exhaust.
Yep.
So mostly the intake side.
Yep.
But because you've got both of them now, you're not playing against a restrictor for the exhaust. Absolutely do that. I'm very, very keen to see what the outcome.
Yeah, that's right. We'll get to those things. There's once we get to that end of it, there's going to be all sorts of potential engine improvements and upgrades that we might want to start doing, but we'll cross those bridges when we get to them.
So the key for me is taking it in stages, baselining every step, both the naturally aspirated side, then the E-turbo, mapping the E-turbo side, bench testing it, creating our turbo map for every ERPM of the turbo, for every restriction from 10% through to 100% of the throttle body, create that performance map for the turbo, and then when we build the motor, apply that same baseline, which is this curve, tune it down to what we think the motor can actually withstand, take it on a dyno, get the fueling tuned up to suit that, and then once we've got that baseline done, we can then play around with cam timing and we just see what the torque curve moves like. It is only 393 cc's.
Yeah, that's right.
Sorry, 600 cc's. Anyway.
Yeah. Oh, wow. Really, really cool. Really interested. Really, it's going to be really interesting to see what sort of horsepower we can get in these lower RPMs and what the engine can actually handle at those RPMs. I don't know, I guess no one's probably really pushed these little engines in that kind of way.
No, that's right. Yeah. I mean, ultimately, if you get your fueling right and you make sure that you're not, detonating the motor and you're not leaning it off, you get that balance just right. That's about as good as you could possibly do. We're running E85, which is a high octane fuel, so you can bring on some timing where you couldn't have when you're just running pump fuel. It also helps with the cooling effect a little bit. But ultimately, things like your conrods, your shell bearings, anything like that that's where your limits are going to be, and you know, we don't really want to destroy it on the first day out.
No. We'll stay away from that. We have a second bike we can play with when we get to those sorts of stages.
Yeah, that'll be our build bike.
Yeah,
this one's virtually a brand spanking new engine, as you mentioned in your earlier video. It's only done a couple of hundred Ks. The other bike has done about 30,000. So that motor there is the rebuild one. I think we'll work on doing that. That's probably where we'll introduce cam timing and, you know, forged rod and a few other things like that to give it a little bit more strength internally. Cool.
Wow, so exciting!
So excited about this.
So yeah. No. But we've got engine running. We've got so basically in the next 2 weeks we've got we will be bench testing the turbo on the electric motor.
Correct.
And mapping the compressor
against all the parameters.
Yep. So we know what it can deliver at what RPMs, and we know how to tune it.
Yeah. So all those parts arriving probably next week sometime. I'll do a bit of assembly.
Yep. And then
get the controller running.
Yep.
Set up a whole new little monitoring platform, so we can monitor all our baselines on all our bench testing. Capture all that in a series of files, analyze it all.
Yep.
And then apply it to the bike.
Yeah. Well, apply it to the bike. So putting it on the bike there'll be a little bit of there's a bit of work in that, just doing all the plumbing work.
Yeah.
But
for sure. But that's that's all just a matter of finding the space for everything. And then locking it on, put brackets here and there. The battery's got to go somewhere. The controller, the circuit breaker, the motor, the turbo, all that sort of stuff. But we've sort of thought through where all those things are going to go.
Yep.
And
decisions are made.
Yeah. Provisions are there. But yes, very exciting. Very exciting.
Yeah.
A lot of little pieces to the puzzle to get there.
Yeah.
But I think it'll all come together quite quickly from here on in.
Yep. So. And I think as far as like it's easy to be overwhelmed and try and solve all the problems before you have them. But I think once we put the thing together and you start running it, I think what we've got, everything will start falling into place, and the things we haven't seen will become obvious, and we'll be able to address them.
Yeah, and like all those things, you solve those little problems as you go.
Yeah.
But as long as you know your baseline where you started from and everything was stable there, whatever it is that you've introduced that causes a little bit of a problem, you solve them as you go.
Yep.
So and then that becomes your new baseline sort of thing. So, yeah. Okay.
Very good. All right. Well, very exciting. Let's we'll get cracking and meet up next week and do some more videos.
Yes, absolutely.
Hopefully we'll have a video. Well, we'll see how we go. We might have a video of something spinning and something running.
Yeah. Well, I'll get busy on that. And as I said, as all the parts turn up, I've got to build our bench test. So I've done some of it. I've got the new controller and all the CAN bus working. So I've just got to do all the plumbing for it all,
Yep.
So we'll see how we go during the week.
Very good.
And then we'll catch up when that's done.
Yeah. Very good. Awesome. Thanks, Richard.
Okay.